It's a sort of massively looking question because lots of numbers in that question, but the solution itself almost immediate. So I need to open these numbers, lots of numbers in that question. I'll open them and I'll make my comment. So in that question, you're given two planes in four-dimensional space. So you can imagine how many numbers you have to type in or copy from the slide. So here's my two planes. In four-dimensional space. Both planes are given in four-dimensional space. We don't have any other option. We can only present planes in a vector form. We don't have any Cartesian form or any point normal form. Well, actually, we do have but it's for different planes, for hyperplanes. Question 35 goes to ask whether these two planes parallel in this four-dimensional space. Now, even though we have lots of numbers on the slide, structurally, the question is very simple. And I'll present you the structure of the question first. So I'm going to introduce symbols for everything, for every vector which is on the slide. So let's just imagine my first equation has first plane has an equation like so. So you see I just call this vector x0, a1 and a2. These are the abbreviates for these two vectors. And that's the vector equation for my second plane. x1 is the position vector, and b1, b2, these two columns. So if I would like to test whether my planes are parallel, the test will sound like this. You have to see whether one of these vectors parallel to these two, and whether the second vector is parallel to these two. Individually, this task we solve with you a few times, testing whether a vector parallel to the given two. I clearly remember I did at least twice this in class. And when we did so, the main test is this. We have to test that the vector b1 in a span of a1 and a2. So b1 parallel to a1 and a2, b1 in a span of a1 and a2, and b2 in a span of a1 and a2. These two tests together, this is your test for two planes being parallel. But I have, well, this case being parallel includes the case where they coincide as well, of course. I mean, if you want to see that they're parallel and distinct, we have to make, on the top of this, you have to make one extra test to distinct them. But it's a different story. From the point of view of Gaussian elimination or augmented matrices, you have to see whether this system, whether this matrix is solvable, this augmented matrix is solvable, and whether this augmented matrix is solvable. You see, I use my notations again as columns in my matrix. Or, because my matrices, they share the same left-hand side, from the practical point of view, I should address this matrix and see whether it is solvable. You see how far we can go without writing a single number if we extract the structure of the question. And so effectively, when I will start my test for these two planes to be parallel, I will write this augmented matrix, and I will see if this matrix is solvable. After I finish the structural analysis of my question, I can start doing the computational side. Again, I'm not going to lie to you. I use the maple to do that. It's a huge matrix. I don't have a patience to finish that with the hand, especially when it's week 12 of a semester. So here's the matrix. I just copied my columns into that matrix. It's not so big. 4 times 4, we did the determinant of 4 times 4 just last week. I took it to the row echelon form with a maple, and that's where the question stops, because you see I have lots of pivots. I have actually 2 pivots on the right hand side, which means that none of the systems are solvable, and so my planes are not parallel, and the question stops right here, which is a bit unfortunate because I was hoping to go a bit further. I was hoping maybe the question will give me the case where they are parallel, but I double check every number. It seems that I copied everything correct, and my matrix is truly, my matrix is correct, and my planes, they are not parallel. That's a bit of a frustration, actually. Any questions?